Your immune system has two big problems. First, when it sees a new pathogen for the first time, it's slow. Second, once the infection is gone, it needs a way to remember what it fought. Vaccines exist to solve both problems at once. The core idea is simple. A vaccine gives your immune system a safe preview of a pathogen, or just a key part of it, so the real infection can be stopped quickly later. That training happens through cooperation between two systems, innate immunity and adaptive immunity. Innate immunity is fast and general. It reacts within minutes to things that look dangerous. Adaptive immunity is slower but precise. It recognizes specific molecular shapes and builds memory. Vaccines mainly aim to train adaptive immunity, but they rely on innate immunity to get started. What exactly does the immune system need to learn? It learns antigens. An antigen is a specific molecule, usually a protein, that the immune system can recognize. The immune system does not remember whole viruses or bacteria, it remembers small molecular features on them. But antigens alone are not enough. The immune system also needs danger signals. These signals tell it that this antigen matters and that it should build a strong response. That's why many vaccines include adjuvants, which are added specifically to trigger innate immune activation. After a vaccine is injected, the first thing that happens is local inflammation. Immune cells at the injection site detect the vaccine and release chemical signals. Blood vessels open up, more immune cells arrive. The soreness and redness are part of the message. They are telling the immune system to pay attention. Next comes the teaching step. Specialized cells called dendritic cells capture the vaccine antigen. Inside these cells, the antigen is broken into fragments. Those fragments are displayed on the cell's surface and carried to nearby lymph nodes. This is how information moves from innate immunity to adaptive immunity. In the lymph nodes, dendritic cells meet T cells. Most T cells ignore the antigen. Only the few with the correct receptor respond. When they do, they activate and multiply. Some become helper T cells, which coordinate the immune response. Others become cytotoxic T cells, which learn how to kill infected cells. This step is crucial because T cells control the quality of the response that follows. B cells are activated next. A B cell can bind an antigen directly, but to fully activate, it usually needs help from a helper T cell. Once activated, B cells start producing antibodies. Early on, these antibodies work, but they are not very refined. Then the immune system improves them. Inside structures called germinal centers, B cells undergo repeated rounds of testing. Cells that bind the antigen better survive. Cells that bind poorly die. Over time, this process produces antibodies that stick tightly to the pathogen. B cells also switch antibody types, producing forms that are better suited for long-term protection. When the response peaks, most active immune cells are removed. What remains is memory. Some B cells become long-lived plasma cells that continuously release antibodies into the blood. Others become memory B cells, ready to respond fast later. Memory T cells also persist, circulating through the body or staying in tissues where infections usually begin. This memory changes everything. During a first infection, it can take a week or more to mount an effective response. After vaccination, a future exposure can be controlled in hours or days. Antibodies can block the pathogen immediately. T cells can eliminate infected cells before the infection spreads. Different vaccine technologies train the immune system in different ways, but the logic is the same. Live attenuated vaccines closely mimic real infections and tend to produce strong, long-lasting immunity. Inactivated and subunit vaccines are safer for some people, but often need adjuvants and boosters. mRNA vaccines instruct your own cells to briefly make the antigen, which leads to strong antibody and T cell responses without using the pathogen itself. Boosters work because memory cells already exist. When antigen is seen again, the response is faster, stronger, and higher quality. Antibodies improve, memory deepens, protection lasts longer. In the end, vaccines work because they turn the immune system's slow learning process into preparation. They don't fight disease for you, they teach your immune system how to do it better before the real test arrives.